Hello everyone, we just started the recording, so let's get started. Today we're going to be talking about advanced technology, doing some HyperLynx simulation or some high-speed SerDes type analysis with HyperLynx. This particular webinar has been sponsored or put on by Oasis Sales and Topology. So Oasis Sales, they're a reseller for Mentor Graphics. They've been working with us for years. They cover, as you can see at the bottom, a whole large list of states. Most of it's in the middle of the U.S. and really good at helping out customers to find the solutions they're after. Also supporting us or putting this event on, we've got Topology. They've also been in this business for a long time. They're pretty much on the East Coast, as you can see. By those states. Actually, we got a map right here to kind of show you the different areas. So Oasis covers all these states in the middle and Topology there on the side. So again, they're resellers for Mentor Graphics. They sell our tools, which include the paths, the Expedition, HyperLynx tools, as well as some other tools that they may carry that are not Mentor tools. But that's a little bit about them. So today we're going to be going through some analysis with HyperLynx. Looks like there's also an upcoming seminar October 18th that you might want to get in on for the HyperLynx DRC tool. So let's go ahead and get started. If there are any questions, go ahead and put those in the chat screen and mute your microphone so that we can keep things quiet as we move along. All right. So yeah, my name is Sherwin Davenport. I haven't mentioned that yet. I'm an application engineer with Mentor Graphics, and I'll be doing the presentation today. That's actually a picture of me right there. We're going to be going over some new features that are in the HyperLynx VX.2.3 release, and I'll walk you through those. As far as the agenda for today, first off, we're going to go over the HyperLynx family, sort of an overview of what we actually have out there. There's a lot of things now under the HyperLynx name. And then we'll move more into a focus on SerDes channel analysis, what the current challenges are, and how to go about analyzing that. Then we'll bring in some advanced solvers a little bit at the beginning and more later on. Talking about what we can do with those and where they fit into the analysis flow. And a bit of a summary there, and we'll wrap things up. So we'll go ahead and get started with the HyperLynx family here. So looking up here in this top corner, the list of the different types of analysis that HyperLynx can now cover. We started off with the HyperLynx SI. That was the original mainstay for HyperLynx. Power integrity tools were developed on top of that. Then some other technology that we had, the design rule checker tools, those were incorporated or included in the HyperLynx family and enhanced upon. Then we needed full wave solvers to address the more complex needs that today's analysis have. And that included things like the fast 3D electromagnetic solver. And then we've also got thermal analysis. We'll go through that in a little bit more detail here. So, but the intent for all this is to come up with ways to help you do virtual prototyping, to try and come up with solutions before you go to the expense of actually building physical prototypes. We're looking at just tools that are easy to use. If you have a analysis tool that's difficult to get going, easy to forget how to use the knobs, it's not going to be of much use to you. So we definitely want something easy to use, easy to pick up for the engineers, for even PCB designers, but of course being high-tech enough for the specialists to also use and get the answers that they need out of that. And then, of course, we want to help you get some product differentiation, help you get, meaning we're looking at superior performance and superior quality for your designs and you kind of need some tools to help you find that space, and we're here to help provide that. And then the other thing that you're trying to do with your designs is to optimize cost, size, and time to market. So again, we want to help you with our tools to accomplish that target objective. So in that space, or the space we're talking about today, we've got HyperLynx Signal Integrity. There is a pre-layout environment we call Line Sim. This is a place where you can come in, sort of a scratch pad space to try out different scenarios, see how things might work. For this example here, we've got a couple driver pins. It's a differential going through a package, and these parts here represent traces on the board. We've got a via that we're going through, then some more traces, another via, and on and on. So the idea here would be to come and mock up something to get an idea of how you might lay out this differential pair and what are the limitations that you can go with. So you might take like the manufacturer specifications for how they say to route things, and then try and incorporate things for the design that you're trying to do. Put your own stack up in there, different routing concerns that you have, maybe different connectors, and try that out and see if you can still meet the signal integrity needs that you are after. And then you can go off and specify those things as rules for the layout designer. Once the layout is done, then we've got another tool called Board Sim, which lets you take that routed board and run the same type of simulation, only on routed information, to see how you did and make sure things actually are working to the specs. So with the signal integrity, we've been focused on the traditional signal integrity tools. That's noise, crosstalk, timing. Then, of course, DDR came along, and we needed good tools to deal with that. That was a pretty big challenge at first. You'd have these critical timing buses going real fast with the DDR. And the way to analyze that was to get some time of flight information from the signal integrity tool like HyperLynx, take that data back to a spreadsheet, and do that for all the data bits and the clock bits, and then compare that within the spreadsheet to figure out whether you're meeting your setup and hold times. So we've embedded that type of intelligence into the tool to enable you to just select the bus, run the simulation. It'll come back and tell you whether the bus is passing or not, or which bits are not. And then further on, we've got now the SerDes technologies. There's lots of different things going on in that space, and we need some tools specific to help out with that. So anyway, that's the area that the HyperLynx signal integrity is focused on. Then we've got the additional set of tools under power integrity. There's two different aspects to that. One is the DC drop analysis. So the idea here is if my chips were pulling at their maximum power, how would the power plane react to that? I mean, I'm supplying 1.5 volts at the power supply section, but with all that power being pulled, there's various resistances in the power distribution network that are going to cause that to drop down. Am I going to get the right voltage at my chips? Also, I want to look at current density. I have areas that are extremely high in current density, which is going to cause heating and possibly some failure in that. So this is a tool to help you analyze that and look into those types of aspects. This plot right here is the current density plot. The red areas are high current density, so they could probably use some additional copper there. This plot is the voltage drop, so we're coming in at the high voltage there, and then as it graphically and color-codedly drops down to the lower voltage level, we can see where the big drops are. The gray area would be the threshold, so in this case we're seeing that this is not meeting the power needs for that particular power distribution network. But that's just kind of at a DC or, flip it on, worst case type analysis. Then the next thing to look at is, okay, well, I'm going to put a bunch of capacitors all over the board to help keep that power plane stable. because power isn't pulled at a constant. It's constantly pulling and then not pulling, and it's on and off kind of thing. So how are the capacitors going to manage that? And you put those decoupling capacitors all over the board. Did you put them in the right places? Did you choose the right values? So this will be a tool to help you go in and analyze that. You can get frequency plots to see how the values are working out, whether you need different values. And then we've got graphical plots that let you see whether the placement is able to keep those ripples down around the part, so whether you need to move the capacitors closer in. All right, so that's the power integrity tools, another set of great tools that we've got going for you. Then there's HyperLynx DRC. This is an interesting one that actually doesn't do simulation. It's just looking at graphically how things are put together. And this originally started with the EMC, EMI area of design checking. Doing full EMI analysis on an entire board is it's problematic, and it's something that computers even today take a long time just to get a good model of the board itself as far as electromagnetic model goes. And so just getting the basic model and then trying to simulate feeding in some sort of signal, it just takes too long to actually set up the simulation and run it to be anywhere near practical. So the thought process was, well, why don't we just go look at the board and find areas where there's going to be problems and fix those, and then we don't really have to worry about whether or not we routed things that are causing radiation. We find those things and fix them. So for example, here we've got some traces that you can see running over a gap in the reference plane. So these areas here, basically they become antennas. You've got exposed copper here, radiation could come there, but then particularly on the return path where you can imagine the power trying to pull back through here, it gets to this point trying to get that current flow in the opposite direction over this gap. It's basically just going to jump from here to there, which is essentially becoming an antenna. Number of different things, rules that we've got like that we can look for structures and see if there's something that's just routed in a way that's not going to work. And you can narrow it down to just look at particular buses. Obviously, I don't care if my analog nets are doing this, but my high-speed digital, I don't want this kind of stuff going on. So if there's kind of things like that you're looking for, not even in the EMI space, but in other areas, we've got a lot of rules here that cover those spaces. So let's look at that a little bit here. So here's some signal integrity rules. So things like looking at differential pairs. Do we just meet the impedance rules that we'd set up? How about symmetry? You routed that differential pair to your routing constraints, but did you actually get them so that they're exactly the same length and they're symmetrical throughout within a certain tolerance range? So, you can look for those kind of things, other topology settings for things like DDR perhaps. Anyway, a lot of rules for SI. Power integrity, there's some things we can look at there, your capacitor placement, capacitor values. Anyway, so a few things there in that space. EMI, as I mentioned, we've got those, but a lot of different things. Look for metal islands, vertical reference plane changes, lots of things that can cause EMI problems, and to look for those. And then we're expanding this out with our latest release with some safety rules. This is high-speed creepage, not high-speed, high-voltage creepage issues, and then some additional analog rules coming on. So again, if there's things that you just typically go look at the Gerbers, trying to look for problems with the way things are routed and analyzing your critical nets that way, why not automate that process? And then you get a stronger feeling of confidence that you've actually checked everything. So that's where the HyperLynx DRC tool comes in. Then we get the advanced solvers, a different set of tools, still looking at the high-speed problem. This comes into play with these extremely high-speed SerDes lines. We're up into the multi-gigahertz range, and you know, the basic transmission lines were fine up to maybe a gigahertz, but we get up past that, and these little via structures need to be paid more attention to. Might have some stitching vias around there that are helping control the impedance as we go from the bottom layer to the top layer. And in cases like that, we want to get a full 3D model of that section of the board, and that's where the advanced solvers come in, is they're able to get very accurate models of portions of the board like that. And then let's go on and look at a picture of that. So we take this portion of the routed board, extract that out, and generate an S-parameter model off of that to properly model that section. Anyway, so that's really going to help out with the accuracy of how things work out. We can take that S-parameter model back and maybe plug it back into LineSim here. So we've got the trace coming along. This is still a package. We've got some routed traces, and then you might have connectors. But anyway, so we can put in those S-parameter models for those via structures at different points along the line to represent the more critical portions of the transmission line. But still, to speed things up, we'd like to use basic transmission line models. Not a lot's changing in those areas. They don't need the critical 3D modeling that these other goofy spots might need. So doing a hybrid approach to doing the analysis really speeds things up and makes simulation feasible. So back to the view of the routed board. Again, we'll get the 3D models at these ends where we've got some odd critical stuff going on, but the traces in between, they can be handled by your classic 2D type transmission line modeling, and we're still getting really accurate results with that hybrid approach. So, you know, it's kind of an integration between the HyperLynx SI tools and these 3D field solvers to get the job done. All right, so moving on, we're going to talk a bit about the SerDes channel analysis problems at this point. So just looking at this plot, you know, back in the day, we're talking about USB and USB 1.0 and 1.1 and maybe some faster Ethernet stuff. A lot of people wanted to simulate that, figure out what's going on, but in a lot of cases we can just maybe go with some guidelines and get that sort of thing routed, figure out what's going on. But you can see as time's progressed, the number of different types of serial protocols have grown by quite a bit. There's a lot going on, and you might have been pretty good at USB 1.1, but what about USB 3.0? Or maybe someone says, hey, let's throw in a PCIe 4.0 bus. There's a lot of things that someone has to go off and read some manuals and analyze to figure out, what do we even need to do here to make this be a nice clean signal? So lots of stuff to figure out there. So another way to look at this plot, originally looking at less than 1 gigabits, we're looking at trace lengths, impedance, and some crosstalk. Things are still pretty simplistic, but you can see as the speed goes up, there's more and more things that we got to be worried about. We're looking at insertion loss and return loss, and you know, just little bits of skew between the trace lengths become a bigger deal. And then at these really high speeds, surface roughness, so just the roughness of the copper traces, we need to model that to get an accurate model of what's going on. Concerned about fiber weave in the dielectric. So yeah, the faster you go, the more of these little things we could ignore at slower speeds all of a sudden become a critical part of the simulation. So we need some way to kind of piece this all together, figure out how to model all this, and then in the end figure out what's going on. So again, those are the challenges you're dealing with. All these different protocols. This may be an area where you may not done a lot of work before. You just routed to the manufacturer standards and things worked and you're happy. But now you got to kind of put on your thinking hat and figure out what's going on in both the SI space and the EM space. So that's where we want to step in and help out to simplify this. So some questions to think about as we go through the rest of the presentation for today. How do you know if the implementation is possible? We'll come back to these questions later on and kind of point out how we can help you out with these things. But so you got something you got to do. Can you even make that work with the boards, the designs that you're working with? How much variability can I have in the layout? Layout guy says, you know, I'd like to go a little bit further, or I need to jump to a different layer or put some vias in. How's that going to mess things up? What if I don't have models for my drivers or don't even know what the drivers will be yet? So this is a pretty common problem, especially as people are jumping to newer technologies. The models may not be out yet, or vendors may be a little bit hesitant to put models out on the public domain, so you got to sign NDAs and get all that kind of stuff lined up. But you kind of need to get your design moving. So what do you do in those cases? How do I quickly validate an interface to a protocol standard? So someone tells you there's a protocol standard. How do I know if I'm meeting up with that? How can I model a long, high-speed channel with 3D features in a reasonable amount of time? So again, anytime someone says you need a full 3D model of this, you got to equate that with a long time. So even small via structures, to get a full model of that might take an hour to generate that. And if you've got multiple high-speed channels, just creating the models for that is going to take quite a bit of time, and then you got to run the simulations. And, so how do we speed that process up? How can I easily find problems in many SerDes channels in my design? Some people are coming back saying we've got 50 SerDes lines on this board. It's going to take me forever to go in and carve out all the areas I need 3D models for. That's a challenge. Is that even worth doing, or should I just build a prototype? So how can I model and simulate hundreds of SerDes lines? So kind of the same problem there. So yeah, we'll come back to these questions, but these are things that I think a lot of you are running into. So let's look at what we've got on our side in HyperLynx to help out with that. So we've got pre-layout design space exploration with a 3D Explorer and sweeps. So this is part of the advanced solvers. This is a way, I'll talk more about this throughout the day, but it's just a way to say, all right, I need a via structure. I'm not sure what's going to work. Let's put down a basic one and then sweep some parameters and see what type of via model in this case would work. Pre-layout compliance testing with SerDes Compliance Wizard. So again, we've got protocols that the vendors are putting out. We got a wizard that'll go ahead and tell you whether or not you're matching up with that. Post-layout automated 3D model extraction. So you got the routed board, not sure exactly what sections to turn into 3D models. You can set up some parameters or use the defaults that we've got. We'll go off and find the areas and get those all set up and ready for simulation to turn into 3D models. Post-layout variability analysis with 3D Explorer. Again, you've routed the board, you've got a structure on the board that you don't think is quite working out. Take that off to our full wave solver and sweep some parameters, figure out what's going to work there. Post-layout compliance testing, so just like the previous compliance testing, only doing this on routed boards. And then doing post-layout IBIS AMI simulation. So that's the full transient analysis. And then there's other tools in that space to help out. But so creating these pre-layout topologies, we need structures, transmission lines, vias, connectors, BGA breakouts. We need some way to connect all this up together. We provide that with the lines in tools, and then ability to look at various different technologies. We get that structure there for you. So the process for this, just kind of working through a standard workflow. You might start out with line sim, building up a basic topology, estimating lengths, throwing in connector models if you can get those, and then of course blocking capacitors and driver receiver models. and then get this down there to try and figure out, okay, what's how close is this to what we think is going to go on. Then let's refine this a little bit more with some 3D VIA models. You're not going to just use a basic VIA model for this. You're going to maybe add in some stitching vias. So you can either just use this is a basic 3D model. There's some parameters you can try out moving those vias around, or you can go into our 3D Explorer and really sweep lots of parameters and try and figure out what's the best structure for this. Anyway, so we come up with a desired VIA structure, put that back into the line simulation. This is the sort of the interface for the 3D Explorer coming in and sweeping different parameters. This could be used also on the DC blocking capacitors. How am I going to mount those? What's the appropriate way to do that to get the best effect out of that? Because there's a lot of unwanted impedance that shows up in this. Anyway, so we don't want to get that stuff in there, or at least get it so it works appropriately. All right, so then we can bring all these various S-parameter models that we've generated with the 3D Explorer back and run some sweeps with the full topology we've built up, figure out which one of those is going to work best for what we think might be going on. And then we can also take that and do some compliance checks to say, okay, well, we've got something that looks like it ought to go. Does that meet the protocol standards that are defined for this particular bus? Because you know, the idea here is you don't always know what's going to be driving things. If you got like a USB plugging into your computer or whatever, that's somebody else's drivers. We want to take the worst case type of driver or receiver and set that up in the simulation and just make sure it meets the protocols that protocol values that are defined for that particular interface. And then running a IBIS AMI simulation. So this is the transient, and this also includes bit error rate estimation. So we'd run a worst case bit pattern through the interconnect and then use some statistical tools to estimate what the bit error rate would be out to 1 million or 1 billion bits. That's what these plots over here are showing on the side, that bathtub curve there. All right. Okay, so then we've got this, we make this pre-layout system schematic larger, adding in other traces, seeing what sort of crosstalk might be acceptable, and work with those type of parameters. And then from there, we're going to define our constraints for layout. So someone's got to go actually route this out. So we'll take what we've learned from our analyses and embed those into whatever constraint system you're using. HyperLynx being a CAD agnostic tool, you can go back and plug this into these values into whatever layout tool you're working with. We just give you the ability to figure out what good values would be. In this case, we're showing how we can embed those into our Expedition constraint editor. But, so yeah, that's the next step, and then obviously we go off and route that, and then we can use our DRC tool before we actually get into simulation to just go check what we've routed graphically and see if there's some obvious things that should be rectified. Maybe there are things that your layout constraint tool couldn't handle, or you forgot to build layout constraints for that. We can catch those with the DRC tool and go back and tweak those things before we move on to simulation. Then we get back into the simulation aspect, take the full routed board, maybe get multiple boards, connect those together. We can do that with HyperLynx, add in the connector models, run the compliance analysis on that entire topology, see if we're going to meet up with the values we need there. And then if that's good, it's a pretty quick simulation there, we can go on to the full IBIS AMI simulations and get more detailed and accurate results out that way. So yeah, then we can sit around and analyze the plots and see how we're doing. You know, we'll talk a little bit more about S parameter plots and how those work into things. That's actually the next topic here, are S parameters. And I wanted to throw this section in here because I recognize a lot of people don't know a lot about S parameters. I mean, it was kind of a new idea to me. That's something the RF guys are off playing with, but in the digital world, it's not something we've spent a lot of time with. So what are they? How do you look at them to get some meaningful information about them? Let's start with a real basic S parameter plot. This would be, it looks like probably a via to me, something pretty simple. We've got two different plots here. Looking over here in this corner, this is telling me we're going from port 1 to port 1 and port 1 to port 2. So it's a two-port S parameter model, so just an in and an out. The one-to-one, that's return loss. So that's when I feed in energy, how much of that bounces back. If we look at that one, that's going to be this red plot here. If I just put in, you know, DC, so it's frequency of 0, I don't expect any of that to return. I expect all the energy to go from the port 1 all the way to port 2. So very little of it is coming back. But as the frequency goes up, we do start to get some reflection back to pin 1, and that goes up and up. And you know, this area, it's not doing very good. So that's what return loss is. Insertion loss is how much gets from port 1 to port 2. So we're inserting it, we want it to get to the other end. How much of that is making it all the way through? That's insertion loss. So again, at DC, we expect all of it to get through. So we're getting a lot of energy on the other end. But as frequency goes up, there's more and more things impeding the signal from getting over there. And we got a low point right at around 15 gigahertz, where there's quite a bit that's not making it to the other end. Anyway, so that's just basically looking at that. So if I were to say I had a via built like this and I was going to be using it at, say, 5 gigahertz, I'd say, you know, that's probably pretty good. 5 gigahertz, we don't got a problem. But if this particular via was something I was planning to use at 15 gigahertz, I'd want to go look at a different via pattern. That's not going to be good for that via. I mean, most of the energy is just going to get reflected back. So with that information, let's move on to some more complex S parameters. Maybe a full channel here. We've got two different traces. This is the return loss we're looking at here, so how much is coming back. Again, at low frequencies, not much comes back, but as frequencies go up, more and more gets reflected. So if I'm looking at these two different traces and trying to decide which one's the better one, you know, if I'm functioning, let's say 5 to 10 gigahertz, I'd say the green one's a better solution for that space. And red one's not doing too good. There's more energy getting reflected back to pin 1. And then looking at the insertion loss, this is how much energy is getting through. Again, between 1 and actually up here to about 12 gigahertz, the green is performing better. More of the energy is getting through to the other end. We've got some issues here just below 10 gigahertz, where a lot of the energy is not making it through to the other side. So that's how we work with S parameter models. A little bit more detail on that, because you can see those plots had more than just one circle. I mean, it wasn't the plots, it was the little control box there. So to explain what's going on here, this upper corner, that's differential to differential. So that's, again, if we look at the differential pair, we're feeding in differential signal, how much of that as a differential gets reflected or gets all the way through. The other thing we might be interested in is differential to common. So that's this mode here. So this is maybe feeding it in as a differential, but some of it is actually common mode. So as one side of the differential goes high, the other one is actually going high too, whereas with differential, you wanted it to go low. So some of the energy is following the other, so it's common. So we don't want a lot of that, and that usually occurs because you've got different lengths of the in the two differential pairs there. So obviously the top corner, the differential to differential, that's the most important. That's where we're going to spend a lot of time. But it's good to also check out the differential to common mode. All right. So I've mentioned that there's different interconnect characteristics. These protocols or specific metrics that they use. They call them figures of merit. These are some of those things. So these are things that are specified for a particular type of interconnect, and we can go off and make some measurements to figure out whether or not we're going to be compliant or not with that particular interconnect. So we'll look more into that later on. First off, though, I wanted to go just kind of through the flow that we've been talking about, get into some demos here of looking at taking that trace and adding some more accuracy to that. So that's the 3D via modeling. So let me go ahead and bring up a line sim design here. So we've got our differential driver. There's a package that differential driver is inside of that. So it could be an FPGA package or whatever. It gets to the board. There's some traces that go along. They change impedance a little bit here, not by much. And then they go through a via to a different layer and then come back up to the top layer and on and on. I'd like to get a little bit more accuracy with this via model here. Right now I'm using some of our more basic modeling, which again was okay up to 1 gigahertz, but above that I need to do something fancier. So let's go ahead and change this to full HyperLynx full wave solver. And because, again, via modeling takes a while to actually go through and model that, we're going to, for sake of time, just jump to a pre-built one. But I'm going to go through and walk through the steps of what we did to build that up. There was just a little GUI here that we had some different things that we can choose about that. So what layer are we going from and to? There's already a pad stack defined here. We can choose different pad stacks, but and we can edit those. So we define the pad stack, the anti-pads, whether it's a common anti-pad, what's the separation between the two. So just defining the via structure itself, individual vias, feeding traces. So I've got some traces coming along that are going to connect to that. I can include those in the model. So how long do I want this section to add in there? What's the angle that I want to come into that? The separation, you know, other items we can tweak there. Stitching vias. So again, I've got my differential via here. If I can get some power stitching vias close by, those can help with the return path and help modify the impedance of this via structure itself. So how many of those do I want? What's the spacing on those? And then now that we've got the physical parameters set up, what type of model are we after? To what frequency are we going to analyze out to? You know, if your design's only running at 5 gigahertz, we may not need to go up all the way up to 50. So let's just get the range that matters here. So in this case, I've got this set to 20 gigahertz. If I click on the View 3D, this is going to go ahead and launch our full wave solver tool and bring up the 3D version of that model structure that we've defined with these other GUIs. So we'll give that a moment to bring that up. Anyway, as I mentioned this, if you do have the HyperLynx gigahertz package, the ability to run the full wave solver comes as part of that license for the line sim side. So we'll get into stuff that's kind of above and beyond that later on. But just getting a little structure like this, again, that's part of the gigahertz package and getting a 3D model of this. So yeah, definitely got a lot of power in that. But anyway, so you got that 3D model, all that structure there. This is the the 3D field wave solver. If you really get into this tool, you can start adding in additional copper and tweaking parameters. But as far as this goes, we just need to run simulation. I actually don't even need to open it here to do that. So let's go ahead and close this down and go back to our HyperLynx tool here. And let's just click on View Model of that via. And that popped up right here in the back. So yeah, that looks a lot like the one we had in the PowerPoint, which is why I figured it was probably a via structure. Anyway, so we've got the reflection information here. 1-to-1 is the red one. Keep that on here, and then the amount that's getting through, that's our insertion loss. So you know, if again we're running below maybe 8 gigahertz or so, I think this looks pretty good for that. Up here, not so much. All right, so I think PCIe Gen 3 probably be okay with this. Something. Just guessing. All right, so that's the model we've got there. So let's just cancel that. We've got this. So we're pointing to that model for that structure. Let's look at this in a broader aspect. So with the whole interconnect included, we'll leave this as the model for that section. It's got a little 3D there telling us that's what that is. We're going to export this out as an S parameter model for the whole trace. We'll do auto mapping, 20 gigahertz there. Go ahead and create the model. I've done this before, but we'll just do it again here real quick. So we'll do with the 3D model and save that, replace that, and then say create. No, wait, okay, so go ahead and run that. And there's the results for that. So let's just rearrange stuff so we can see a little bit better what's going on. Get both of those, and then I'm going to change this to mixed mode, so it's differential. Yeah, so it's you know, below 4 gigahertz, we're okay. Kind of worried about how this is dropping off quite a bit, and then you know the return loss starts to get bigger in this area here. But anyway, so I can see what's happening with that result there. But what we want to know is the difference that VIA has on this. So let's go ahead and minimize that. Come back and close this. Change this so now we're not using the model that was provided with that. And we'll go to the basic model. Then we're going to export out an S parameter model of that whole interconnect. Same parameters as before. This time we'll say no 3D. Yes, we'll replace that one. All right, so now we've got two different waveforms. Let's start out by looking at the insertion loss on both of these. Turn off that one. Turn off that one. All right, so yellow is no 3D. So this is what you would have thought things were going to be like. And then we put a better quality VIA model in there, and we can see things are improved. Up to a higher frequency, we're getting better results. Let's see what it looks like on the return loss side. Do that for this other one here. Switch over. So again, no 3D is in blue, so it looks not as good as red. Better quality VIA, we get better signal coming through there. Now just to step things up a bit with this S parameter model checking, let's go ahead and look at a time domain version of this. So what we're going to do is just send a pulse through this time domain response. Change this to mixed mode differential. The inputs are 1 and 3. Apply. So this is an interesting plot because, although other than this one's higher than that one, most of this looks about the same. I mean, this waveform looks about the same as that waveform. There's just something going along here at this area here. And the interesting thing about this plot is it corresponds with the actual trace itself. So if we look at this here, we've got the driver and then this package. That is this section. And then we've got a little bit of trace, and that's this section. And then we've got the VIA, and that is this section. That has the big change. And then we've got a long section here, that's this 8 inches of trace right there. then another via, and then some more packaging and connectors and so forth. Anyway, so it's just a nice way if I can tell. So if before I looked at the S-parameter model and said it's not as good, there's a problem, and I compare the two, I can plot it out here with the time domain response and kind of see as the waveform goes through from the driver to the receiver, where was that issue at? And we can see that it's with the via. That's what that section of this is. And it doesn't label this as via, but we can look sort of with some intelligence where in the topology that problem popped up. So I mean, I think that's pretty cool. All right. So yeah, we can see then that you know, as I mentioned, that the ability to create that model and do all that we've done so far is part of the HyperLynx SI gigahertz license. So something you can get doing if you have that today. And that model, once it's done, you can obviously look at the time domain stuff like we did, but you can carry that on and now use it with your frequency. Sorry, the other way around. We look at the frequency domain, but we can also use it for time domain, so we can run our simulations using that. And getting out our eye diagrams and setting up eye masks and changing the bit stimulus, so forth, that stuff we can do with that. But looking at S parameters in the entire channel, very helpful, and understanding the mixed mode. So that is the SerDes line sim tool. Now let's go look at the compliance wizards and in a little bit more detail. We touched on this a bit, but what we do here is we are going to just look at different types of interconnects. Right now, it's this particular GUI set up to look at an Ethernet protocol, and there's certain metrics that we're going to measure against to see how that's going to function. And these are the types of interconnects we can work with: the internet, fiber channel, PCIe, USB. You know, we're adding to this list, so it's going to get larger and larger. And then we get a nice report back telling us, you know, how things worked out, whether it's going to do what we needed to do or not. So how does this work? Well, we have the compliance set up. You just go and choose the type of protocol and operating mode you're running under, and just by doing that, there are certain compliance metrics that are associated with that we can measure against. Okay, so that's the first thing. You just choose what you're doing. And then we're going to use a reference transmitter and receiver model. So that means that you don't have to have a model. We're going to use a reference one for the driver and the receiver to see just that the interconnect is going to do its job, because what we're after is worst case transmission and receivers, not just the ideal one that you picked out that you're going to use, but if someone else plugs in something else to your USB connector on your computer, you want to know that you can still deal with that, as long as they're designing to these protocols. So we're going to feed in those worst case transmission receiver packages with the reference transmitter receiver models and set up proper terminations, set up jitter, and then work with the prescribed protocol specifications. Does support adaptive equalization. That's something we get asked now and then. So, you know, these interconnects can adapt their equalization values to work better, and we can support that. That's part of the protocols to bring that into account and take the measurements off that. And then we're going to generate from that some plots so you can see graphically what's going on and how the measurements were made. And we get some in the report. We get values, what the margins are that were measured. And we also get S-parameter plots back, so we can look at those and see how they're performing from that perspective. And then there's also the TDR response that's included in that, so we can see that response there. Okay, so let's go ahead and look at a line sim design for this. So this one's a bit more complex than the last one we were at. We've got 3 different lines. They're all coming through the same 3D model here. This is a coupled vias. Someone felt the need to get some coupling going on, just the via structure they built up. we want to know if we did build like this, is that going to be compliant or not? So we'll come up to Simulate SerDes and check the compliance checks only. And here are the differential pairs that we're going to work with. We're going to go with a PCI 3. That's what we want in this case. We got the driver and receiver, or transmit and receive lines identified. There's a place to do sweeping. So let's say this does work, but I want to know, can I extend the traces? Can I change the value of some of the passive components? Can I change the spacing between the differential pairs some? So I can sweep through some different values, run some more simulations, see if we still meet compliance or not. And then just basics of how we're going to run the simulation, you know, what level of frequency and all that. So go ahead and run that. And this will take less than a minute, but it's going to go through and take each of those 3 lines, again, put on the reference driver receiver, and feed some signals through that, and take some measurements off of that to see whether it would be compliant or not. And again, we're after worst case scenarios here, so it may not look the same way your drivers and receivers would if they were used, but we want to know whether it would just be compliant in a more general, generic aspect. So, all right, so it's just about done here. When it finishes up here in just a moment, we'll get that HTML report up. And the HTML report is just really easy to browse through and see what's going on. All right, so we're done at this point. And up pops our report. There it is. Okay, let's make that a little bit bigger. All right, it says we passed and shows us the measurements that it made, the values that it came to. So all 3 of those lines are good to go. They're all going to pass. We can actually bring up the plot here. Click on that in the HTML report. It's going to bring up the viewer. The light blue area here, that is the eye mask, and it's well within the boundary of the eye that's being created around that. There's a few more measurements down here. We can see what's going on. So everything is happy land here. Let's go ahead and run the, close this down and come back and change this. I want to know what happens if I run this at a PCIe 4. So, you know, let's say the design just got upgraded, or some reason we decided, hey, let's change our protocol. This just came out, or somebody wants 4.0 in there sometime or other. So do we have to change any of the traces, or will the same traces work in either case? So, you know, it's going through the same simulation again to get there. And but as you can tell, this is running pretty quick for a complete compliance wizard analysis. And so far, all I've done is just set up some basic transmission lines and other components with whatever modeling I can to make this as accurate as I can for what I might be routing it, and I can find out whether this scenario is going to work. So great place to come in and figure out what your rules should be for doing the layout. All right, we're done again with the next one, 4.0. How are things looking? Are we going to pass? Moment of excitement here. And let's make this bigger. Oh, we got a failure on this top line. The others are passing, so they're good, but something's wrong with this particular one. Don't know what's going on. Could bring up the eye and look on that, but basically, you know, I'm not getting within the margins that I needed to. So over here, we're looking at, I needed 0.3 unit intervals. Unit interval is, you know, it's the bits are changing at a certain bit rate or unit interval. So what percentage of that, basically? And we're definitely less than that. So that's not good. So something's not good with this. I'll just cut to the chase here and tell you what the problem is. So this is the one that's working down here. This is pretty short. We're less than 1/4 of an inch there. But up here on this one that's failing, we've got a whole 1.5 inches. So if I shorten that one back down, it's going to pass. But maybe I'd take a moment here to then run some sweeps. Maybe that needed to be longer. And so I could run some sweeps on the compliance wizard to say, well, how short do I have to get that before it is going to pass? Anyway, so that is the line sim. There it is, Wizard. Again, we've got a big long list of protocols that you can work off of, and you don't need your driver and receiver models to do that. So if you never get those driver receiver models, you can at least do this and get a pretty good feeling that things are going to work out. Let's look at it now on the board sim side. And again, we've got a couple traces here that we want to look at, but it's now routed traces instead of theoretical traces. And we want to know how it's going to function. So again, we just come over here to the compliance checks under SerDes. There's the nets. We got PCI 3 set up there. 2 nets going, no sweeps. You can see the list of things we can sweep here is smaller. It's because it's routed. Things are kind of fixed. So I can't be changing trace lengths or the trace widths and all that kind of stuff. If I do need to do that, there's still the option to export this whole net structure back to line sim, and then I can play around with things and change lengths. But right now we're just focused on what is. There's a few things though we can tweak, like passive values and stack of layers. All right, so then we'll go ahead and run that one and get the results out from there. And this one's only got a couple traces, so it should run a bit quicker than the last one. But the report we're going to get out is going to be the same as the last one. I mean, the same format. Obviously, it won't be the exact same report. That would be silly. Okay. All right, so we're done with that. We'll get the report here on any moment. There it is. Okay, so do we pass the routed trace with PCIe 3? Yes, we do. So all good there. I'm not sure I showed back with the line sim here. We do have other tabs that have more information. So kind of more measurements that are made here. We can look at that. And then additional information. This is where we can get access to these different plots from the S parameter. So insertion loss, return loss, and so forth. Yep. So and there's that. ER plots are in there anyway. So yeah, very useful. In these plots, you don't, or the reports, you don't need a license to view those. So you send them off, or just make them part of the final design packages documentation of what's going on. Right. So that is the SerDes Compliance Wizard in board sim. So again, very helpful and something you can take advantage of just running that from the board. And just to summarize, trying to get more accuracy with the routed board, we can do back drilling, more 3D models, which we'll go into here in a bit, and then and so forth. So, and as I mentioned, you can take traces back to line sim if you want to do more debugging on that. So then let's talk about the advanced solvers and how that can fit into this to increase the accuracy of the modeling again. So again, we've got the routed board. There's sections here that we want to get more information on. It'd be nice to have some automated way to go in and just grab these more complex sections and generate the 3D regions there and automatically for you. The more times you got to go in and set up all these 3D field solve processes, the longer it's going to take you, and then trying to figure out how to plug that back in. That we want to automate all that. So the way we've approached this is, I mentioned the HyperLynx DRC tool that graphically goes through and looks through the design and finds structures that might be causing problems for EMI and SI. Well, that same engine, we've capitalized on that to go through and look at your SerDes lines and say, hey, this portion in here is a good area to build a 3D model of. And down here in this corner, you can see some of the settings that you can use to help guide the auto selection tool to kind of tweak that, make the areas larger or whatnot. So let's talk a bit about the advanced solvers that the tool does have. So there is the 3D Explorer, which I've mentioned before. So this gives you a way to take a structure, like we can see in this picture down here, and to tweak it, to sweep values, maybe sweeping anti-pad shapes, or the angle at which the traces come in, or the pad stack, or the distance between the traces, or the distance between the stitching views. You can go through and create little 3D structures, sweep through them, create S-parameter models, all of those, see which ones are most ideal, and then you can actually go back to line sim and try those out. This is another aspect using on something like a capacitor here in this area. There's some built-in templates that it comes with, and it's automated, so you don't have to go through a lot of the setup process of setting up ports and so forth. It's just kind of choose the values you want to sweep them, and it'll go off and run that for you. So anyway, it gives you that ability to see which values are the best. So down here we can see coming in at different angles, a little bit different topology for each of these different differential vias that we're coming into at this point. All right, so just a few points on the advanced solvers. There is an S on the word solvers. Sorry about the fuzzy picture here, but we've been focusing on the HyperLynx full wave solver. That's the one that fits in nicely with the HyperLynx SI tools, taking care of the 3D analysis portion. The solvers, the advanced solvers, there is a hybrid solver which can also do the full board in a mixed 2.5D, 3D type environment. That's if you don't have the HyperLynx SI tools. There's still some way to do that. And then another area where some of these engines get used is in the case of BGAs or package modeling. So there's some straight areas, not a lot of changes. We can make some assumptions to kind of speed up the analysis process. And just to point out that this set of tools did come from our Nimbic acquisition. We purchased that company, the previous names, and we've renamed those and integrated them more with the HyperLynx flow. So again, it's a real good way to get highly accurate models, S-parameter models. You can get current density plots and so forth of portions of the design or the entire design if you really want to. All right. And as I mentioned before, it's a good idea to have that ability to do a full 3D in some sections, but sometimes you want to do a hybrid, a combination of that. Probably this screen is a good one to point that out here. So we did some tests comparing full 3D for an entire section like this, and then doing a hybrid where just the ends were fully 3D modeled, and then this midsection was more of a 2D type model, and compared those two results, and you can see here that pretty much the same thing. So it's a good way to quickly get some accurate modeling out of that. So let's go ahead and look at what it takes to get those models set up in HyperLynx. Go ahead and bring up the board here. So here I've got a group of differential pairs, and I don't want to individually go to each one and mark out the sections that I want to model. So come up here to Analyze 3D EM and go to Manage Areas for 3D Simulation. And this shows me the nets that I'm working on, and down here are the 3D areas that it's already found. Now, originally when I brought this up, it was all blank. And I'd come over and click on this Create Areas for Selected Nets. It'd run off and look at the nets for about 5 minutes or so, just saving you the time. I did that step already. It comes back here with those sections. So we can select one of these. You can see there's something flashing down there. Let's zoom in and see the area that it has selected. So that's the area that it's found. And go on to the next one there, another area. So it's just saying, everything in here seems to affect that particular set of traces. So we're going to include that in the final 3D model. If I want to, I can go off and edit that. So this is showing me the points that define this area around there, and the ports that are set up to connect to that eventual S parameter model that we're going to get out. And then here we can go ahead and export that off to the 3D or the HyperLynx full wave 3D field solver. We can view that, and we can hit the simulate button here. I don't even need to come into that area. Let's say I've generated all those, I've looked at these, and they all look good. There's another button here for find matches for highlighted areas. So if I've used the same via pattern multiple times, rather than creating S parameter models for each of those, the tool can go through and say, you know, this via pattern here looks a lot like this via pattern, so let's just use the same model for those two. And so that'll save a lot on the simulation time, because remember, generating each of these models, the full 3D model, could take up to a half hour just analyzing that and going through and getting that ready for simulation. So if I can minimize that by several matches, then good deal. Let's come down and look at this one. This one in black is one that I've already run. And go click on the view model. That'll bring up the S parameter model for that section. And let's go ahead and change that over to mixed mode. So looking at this, I mean, it looks like it's pretty good. The insertion loss staying pretty high most of the time. The return loss doesn't get too high. So that looks like a pretty good via structure across this whole range. So, I mean, that's good to know, but now we want to go back and use it in the simulation, which you can. I mean, and now that I have that generated, if I select that net and run a simulation, it will just include the S parameter for that section of the design. All right, so let's go back again to our presentation here. So again, it's integrated in there. We use a little bit of that HyperLynx DRC technology to find those spaces. You don't need a license for that. It's included in this whole package here. But it's an intelligent way to find those areas and quickly map them out. And then from there, you can set off a batch mode to generate all the 3D areas that you're interested in. Now, there are other products that we could go through and demo. We're not going to demo those right now. The HyperLynx 3D Explorer, which I've mentioned a few times, part of the full wave solver. If you're interested in a demo on that, you can either contact oasissales.com or trilogic.com. Same with the HyperLynx DRC tool as a standalone tool. If you wanted to see a demonstration of that, we can do something along those lines. So let's go through the questions that we had at the beginning here and look at some of the answers that we can provide for you. How do I know if the implementation is possible? Well, we've got line sim. We can try out the implementation, simulate that. There's SerDes Wizard to run simulations on that with sweeps, but there's also the protocol wizard, which is even faster to find whether or not it's going to meet the standards. How much variability can I have in the layout? Well, we can use the sweeps within these tools to try out different parameters to see how flexible we can be. There's also the 3D Explorer. It's part of the full wave solver that we can use to, again, sweep values and see how critical these small structures have to be, how critical they are, and how close they need to match the design. If you don't have models for the drivers, what do? Well, the protocol wizard doesn't need models, so you can still get that good checkbox feeling of confidence that, if maybe your models might not look the same as the results we're getting, but worst case models should be okay. How do we quickly validate an interface to a protocol standard? Again, Protocol Wizard is going to do that for you. How can I model a long, high-speed channel with 3D features in a reasonable amount of time? We've got the 3D Area Manager we showed you. We find those areas, and then after we've generated the S-parameter models, we can do a hybrid simulation, which is pretty quick. I mean, it runs a lot quicker. We're using that hybrid approach than doing a full 3D. and then the pattern matching, so I don't have to create full 3D via models for all via models. I mean, if I'm using the same via pattern over and over again, let's just use one model for all of those. How can I easily find problems in many SerDes channels in my design? That's where HyperLynx DRC can come in and help out. Doesn't need a simulator. Just go ahead and look at the topology, find some pretty obvious routing issues, flag those for you, or indicate which nets you want to go further study with a full simulation. And that's where you come in the last step here, where we can do simulation on all these with the 3D pattern matching and the hybrid simulation approach. All right. So where do we go from here? Next steps, again, if you wanted to, if you want more information, more demos, you want to request an evaluation for the West and Midwest, go to oasissales.com. For the East Coast, go to trilogic.com, and they can help you out with that. If you're interested in the labs came out today, again, go to those websites, find the contacts, and ask them for copies of this. We can get you copies of the labs. The demo files that I was working through actually are based on some lab files, so you can go work through those and see how that functions. There's many other labs that we have that we can get you access to if you're interested in different types of topics. Now, past that, you can go to our support center. If you have Mentor products and you don't have a support center account, you really ought to go get one. There's lots of useful information here. Of course, you can get access to your licenses and see what's going on there. But you can also get access to recorded webinars, white papers, things of that nature. Open up service requests, so if the tool's not working for you or you're really stuck, you can go ahead and open a service request. We've got lots of experts who are glad to help you out with that. And then, you know, we also keep track of the issues that happened in the past. You can go through and look at previous service requests that other people taken out. It doesn't have their names, but it'll have the question and the answer there. We also have mentor ideas. This is a fun idea here. If there's things that you want the tool to do and it just doesn't do it, you can go to the mentor ideas site and say, this is an idea I have. Can the tool please do this particular function? And then you can vote on other people's ideas. So you can go through and see what other people have thought of and vote to put your vote to that. And the higher the number of votes are that a particular item gets, the quicker we can implement those into our software. There's also community sites where you can get input from other users. So lots of things you can get through Mentor Support Center. There's also on-demand training. So if you feel like you need more than just what the Support Center has, we have what we call the on-demand training. We also have the classroom training. It still exists, but a lot of people are moving to more of a multimedia type approach, and that's what the on-demand training provides. So you'd buy a subscription to the HyperLynx training, and that would get you access to many, many chapters on different aspects of doing HyperLynx design. And so it lets you go at your own pace. So let's say you were starting to do some PCIe protocol. We've got a chapter on that. There's going to be some videos on that, some labs that you can walk through to try different things out. So it's very educational and easy to follow along. And you don't have to do the whole thing, you know, spend 2 days in class just to figure out to do some specific things that you're interested in. You can just do some spot learning on the things that you're interested in. There's a bunch more classes that they've got. And again, we'll keep adding to this list. So it covers all the HyperLynx tools. We're adding more and more for the full wave solver now, but continuing to update these other topics and add technology-specific chapters. Here's some stuff on DDR, different ways to set up that, and information about running those. So lots of very useful information, become an expert on a tool using the on-demand training. And if that's not quite enough, we do have some services that we can offer. So like a quick start for HyperLynx DRC, if you purchase that and you're really not sure how to get that set up and going, you can open up a service contract, pay some consultants to come in and help you get started with your design. If there's particular rules you wanted written for the HyperLynx DRC tool, you could pay for that to happen or have someone help you write your own. The DDR tools, quick start there. Anyway, these are just some suggestions of things. So, if you're finding yourself stuck and you want some help on your particular design above and beyond just service requests, we have the ability to come in and help you out specifically with that. So that kind of concludes the presentation for today. Hope that was helpful. Again, contact us if you have questions, and I hope this was useful for you. Thanks. Bye.